I'm Robin Jeffries, and I want to introduce today's speaker, who's talking about intelligent assistance for desktop user tasks. So this is Anthony Tomasic. He's director of the Carnegie Mellon University Master of Science in Information Technology, Very Large Information Systems.
I made it up.
I hope the building
actually
doesn't
made
catch on
that
fire while you're saying
yeah.
that. His research is currently on applying machine learning to the desktop as part of the CMU RADAR program. And his research has been on internet-scale databases, federated databases, and the performance of information retrieval systems. And this is collaborative work done with John Zimmerman, who's a professor in the design program at CMU. So there's sort of the machine learning database aspect to it and the design aspect, and you're going to hear about both of them. So he's been at Stanford and INRIA, so he's wandered around the world and got his Ph.D. from Princeton. So thank you.
Thank you. Thanks for the introduction. That characterizes my background. So actually the Ph.D. that I did was in performance of information retrieval, and most of my publications have been in databases. So my role in this project really is to handle the back end, including the machine learning. John does the front end. Frankly, there are design people here, so I'll preach a bit to the choir, but for non-design people, when I first met John, I had no idea how I could work with him. But after talking to him, I realized that I can't do any work without him. The kinds of stuff we're doing here really is a combination of user interface design, and there are very subtle decisions that you can make at the front end, which actually completely change the kinds of algorithms that you're using in the back end, the kind of reasoning that you want to do. So to build these systems turned out to be a lot harder than we originally thought, and there are a long sequence of failed prototypes. So I'm going to show you two prototypes. One's called Virtual Information Officer, and the other one is called Mixer. Virtual Information Officer is in the process of being commercialized. We're right now plugging into Salesforce.com, and our target user are salespeople. The other stuff, Mixer, is hot off the press. The data I'll show you at the end of the slide is actually part of an experiment we're still conducting. So the size of the sample is n equals 4, and we're shooting for like n equals 12. So here's the overall perspective that we've taken. We see workers, let's say people who are using IT systems, as caught between essentially two worlds. One is email, and the other is these back-end databases. And there's a bunch of stuff that we want to do to support this user. Okay? One thing that we want to do is when you get a request to do some kind of work that corresponds to a task, and here we have a very narrow definition of tasks that you'll see, we basically want to help that person do the task by predicting what is required to do that task and suggesting it to the user. The other thing we'll do is, and that's VIO, in the Mixer work, we're focusing on, again, the same kind of problem. You have a task to solve, but here there's an information gathering phase. So we don't assume that the incoming message essentially contains all the information you need to do the task. Okay, so let me go through the Virtual Information Officer. And this is really designed to give you an understanding of the user experience. And both the user experience has been written up and the back-end machine learning has been written up. But I won't go into any details or almost no details about the back end. Okay, so to be a little more precise, we found that when people use the desktop, they have this behavior. They get a very specific request from someone else. They have to navigate to a form system, search for a particular record, and then complete the task. And by completing that task, we mean editing a bunch of field values, submitting a form, maybe creating a table. You'll see that later on. And then, of course, they have the problem of verifying that the work that they did is actually correct. Given that you're doing that, and an example of an email is, please change my phone number to 555-1212 for instance, a person who's maintaining a website. In the traditional scenario, that person's going to read that email. Their job is essentially to identify the data in the email and translate it into the right form, fill out the form. The form gets submitted to the database. Instead, what we're going to do is stick an agent here whose job it is to read the email for the person, predict what values have to be filled into the form, show the predictions to the user, allow the person to approve and perhaps correct what's going on, and submit that to a database. And we'll show that this shifted behavior from essentially serving as this copy and paste agent to someone who's approving a form increases the performance, the efficiency of the person doing this job. And in fact, gives them a better experience. So here's a real email that we got. We went to someone whose job it was to run a website at Carnegie Mellon. We said, please give us all your emails. And it turns out this guy had carefully squirreled away all of the requests to change the website into a folder because he only did this job part-time, and anytime his manager came across and asked him how much work are you doing on this particular thing, he wanted to be able to prove what he was doing. So this is not an actual message. Because we get federal money, we have to be very careful to anonymize things, remove all the personal information. But when we did the personalization, we didn't change any of the grammatical structure. We changed things like last names and first names, titles, addresses, but the actual language wasn't modified, and that turns out to be key for measuring the kinds of analysis that we can do. So if you read this message, it says, it's from David McCullough, who of course doesn't exist. Hi Blake, my new title is research scientist, and then he gives an address and a room number. And then he says, thanks David, and then he gives a URL and there's a signature. Now if you read this message, he clearly doesn't explicitly say anything about what the task is. It's only the context of the message and who the person is that you can translate this into the actual thing that has to be done, which is update this person's record. So that's the first problem. It's actually hard to build models about what the tasks are. And then just to give you an idea of the target, without VIO, the experience would be to navigate to the modify person's form, select David McCullough as the record. Here you get all of David's information. You see that he doesn't have a title. He also doesn't have an office location. You would put in those values in the corresponding slot here. And the implication from the design of the form is that when you do a submit, those new values would replace the old ones. And that, of course, any blank fields would do nothing. Okay? So here's a little bit of how the backend works, just so people who want a global perspective of how we get this experience processed. These email requests come in, and they're submitted to a model, to an analysis program. This thing contains the machine learning models that we've actually trained. Okay? That analysis will run. It will produce a bunch of suggestions, like what form you want, what instance you want, what field values you want to change, or add, or delete, or whatever, and produce a confirmation form. We present that to the user. You get the email and the confirmation form. The user could do some previewing of the website, and then the user will modify the form, perhaps add some new information, and submit that to an execution module. The job of the execution module, and for people who have built web services, this thing is a standard J2EE Java program that submits SQL to a backend database. So that's the submission to the database, but what we'll do is take a copy of essentially the submitted form, hand it to the learning module with the original document. The job of the learning module is to understand where the data occurred in the original message, supply that as training data to these learning algorithms, which then generate new models to go to the analysis phase. So the key problem here in machine learning is closing the loop between the signal that you want and building the models that you get. And if you do traditional machine learning, certainly if you're doing machine learning experimentation, that is, you're only interested in the scientific performance of an algorithm, what you do is you get a corpus, you go through and write a book. You hand the book out that has the rules of what is a label and what isn't. You get a bunch of people to go through and label everything. You compare their labels to make sure they're correct. That gives you a gold standard, and then you provide that to a variety of algorithms to measure their performance. Here we're not doing anything like that. We're extracting the labels directly from user experience. Okay, so if the user went through and every time he had a modify person request, he selected the wrong form, the system would be very happy to learn the wrong model. So here's the experience that you get in VIO. Here's the original message you saw before. We've augmented that message with a bunch of forms on the right-hand side. And there's this request here that, there's a proposal here that what you want to do is select the modify person form. So what's happened is an algorithm has been run, and based on the experience that it's seen from other messages, it's predicting that this thing is a modified person experience, okay? Or modified person task, okay? And you can pick modified person or you can pick something else in case the machine's wrong. So when we originally designed this page, we didn't have this right-hand side bar. We just had a line that said, here, click here to do your task. And then when you clicked on that, we would simply show you the form, which was the one we had guessed. And then, of course, it was easy to navigate off of that form to another one. We found out that that doesn't work at all. When you sit a user down and he clicks on a link that says, now do your task, and he's presented with the add news page when he's trying to do a modify person, he sits there for about 10 minutes trying to figure out what the hell's going on. So the only way that we can figure out these kinds of mistakes in design is, of course, sitting people down and actually using them. That's an incredibly expensive way to fix design errors. Obviously, with good experience, you can reduce the number of these things that show up when you actually build a system, but that was a real learning experience for me. I had no idea of the kinds of things that would pop out. And so now we're very careful to follow, I would say, almost rigorous HCI procedure. We do contextual inquiries. We do very low fidelity prototypes, including showing people pieces of paper and getting their user experience from that, then doing low fidelity, and then doing implementations of front ends, and then finally fully developed prototypes. So after clicking Modify Person, you're going to get this experience. There on the left-hand side, you have the email. On the right-hand side, you have the same form you had before. But there's a difference. Marked in orange are all of the suggestions that the system has extracted that it thinks are relevant changes to this particular form, and they're marked on orange on the right. In addition, the system has not gotten the room number, RM space 390. The recognizer that's associated with room numbers doesn't function very well because it hasn't seen a lot of examples of room numbers, and it missed it. It didn't suggest anything. The user has typed in RM390 there. That's marked in blue. So of course, what's happened is the user has compared the request he wants to do with the right-hand side form, corrected it, and then submitted modify person. All these labels then are then used as evidence to build new machine learning algorithms. So the system learns with experience. Now, there are subtle problems even on this page. It turns out that when we actually ran a behavioral study, our instance learner, that is the learner that decides which instance you want to modify, made a mistake. It thought David McCullough was actually David Rogerson. And then it's blithely said, oh, there's a new last name here. So if you just clicked submit on this form without looking very carefully at it, you would happily change David Rogerson's last name to David McCullough. So it's clear that subtle mistakes in the interaction or subtle assumptions that the interaction designer has can have disastrous consequences because this is a really bad update. And there are lots of different ways of getting around this. One thing to do would be to build models of unlikely updates and then do outlier detection and try and flag things that you found unusual. Our current solution isn't to do that. Our current solution is to change this thing to say modify person David Rogerson. And it turns out that, at least our belief is that when you're reading this, you're going to know who's it from. That's in your mind. And you're going to read the wrong name. And so it's very easy to detect this particular mistake at this step in the workflow. Okay? So that's the way we've implemented it now. We have to run a whole nother study to figure out whether that actually does reduce errors or not. Okay, any questions? Not yet. Okay.
I have a question. So
yeah.
If they do make a mistake and it's changed later, is there a way to roll back the learning?
That's an excellent question. So right now, what would happen is it wouldn't do anything. It would simply record both. And then the learner would be forced to deal with the question of what that evidence meant for its model. Now, if you made one mistake and then you did it right 100 times, machine learning algorithms are pretty robust to this kind of error. And they'll say, oh, look, one time he didn't choose modify person with this distribution of the input, but the other 99 times he did, so yeah, it's a modify person. Okay. That's a great question. And there would be a question about trying to go back and figure out what the mistakes were. I think that's probably very hard because you'd have to actually understand the true intent of the message. So is it the fact that you changed the mobile phone number? Is that because he got a new mobile phone, or is it because that you somehow missed the mobile phone number in the last message? Something like that. I think that's a great question. I don't see an easy way of attacking it, but I'm going to add it to the list because I'm after great research problems. Thank you. There is another question here. This experience that you've seen, if you want to build it, one way of doing it would be to hire PhDs in computational linguistics and sit down and get a corpus of 10,000 messages and build yourself a very high quality recognition system. We don't do that because we were interested in the scientific question essentially of, for this particular domain, can you get away with doing something that isn't so expensive? So obviously if you have to have a deep AI understanding of what you're doing, you need all of that machinery and it's very hard to do and you need complex models of the target. But could we build something which was a much simpler model? And it turns out that for this domain the answer is yes. We're just building essentially for each interaction a machine learning model to try and produce suggestions for that particular interaction. And there's no explicit engineering or labeling. So we just took the default feature space that we got with the machine learning package and we applied it, and yeah, it's true, it does a really bad job on not phone numbers, on let's say room numbers, because in the 200 messages we gave it, there were only 10 examples of room numbers, so you're not aided in that particular part of the interaction. But it turns out for the stuff that commonly occurs, you have a lot of evidence. It's right most of the time, and it ends up helping. So, and here's the machine learning we use for form suggestion. It's a K-way classification. For field suggestion, we use conditional random fields. And for instance suggestion, we're doing a form of reference resolution. There's an entire paper that documents all this. But the question is, how can I actually know that this stuff works? So we measured it. We took a corpus, we anonymized it. It had a bunch of events, file manipulation, news, people in it. And then we simply sat down with an empty system and used it for 189 messages. So of course, the first time you actually use the system, it's not going to make any suggestions. And these learners are very high precision and very low recall, because to suggest something that's incorrect is much more expensive from an interaction point of view. You have to go back and delete that particular action. And if it simply suggests nothing, then you're simply doing what you would normally do, right? Which is fill out the form. So we go through, fill out the form for 189 messages, run these models, and then simply test the held out messages and count how correct they are. And we're going to run these metrics incrementally. There's a lot more data in the paper, and I've got more slides that show you the results. But the answer is here at, I'm not exactly sure, this looks like in the mid-40s or something, 75 or so, we're going to stop this labeling procedure and run the algorithms and test how well they do. And you can see that depending on the algorithm, you get a separation in performance, but they're all climbing over time. This metric over here is mean reciprocal rank. So if we suggest the correct form first, you get 1 point. If you suggest the correct form second, you get a half point, et cetera. Third, you get a third of a point. And then you just average over all of the test set to see how well you do. And we're approaching like 95 with the best combination of algorithms. And this is decision tree, maximum entry, the usual suspects here, SVM, boosted decision tree. So it turns out that if you ask salespeople, for instance, how many emails do they do in a particular day, it's like 30. Is sort of an average from one set of people we talked with. And so after a few days, the system is going to be doing very well. And because it's high precision, it's actually going to be only producing suggestions that are correct. OK? Now, all of that doesn't matter, because it's interesting to note that you can actually extract labels from the environment and run machine learning algorithms and measure how well they do. But the ultimate test, of course, is whether the system actually helps you. Right? If it slows you down or it's irritating or something like that, people won't use it. So we're going to do a between subject experiment. We take 20 subjects. These are people in the CMU community, not only students, but other people who sort of show up and do experiments sort of for fun. And we're going to give them 20 training tasks because we are interested in skilled performance. And then we give them 8 real test tasks and measure a variety of things. accuracy, time, their perception of the experience, that kind of thing. One thing that we found, which was very important, was the incentive function. So if you got an undergraduate and you say, here's $10, come use our software for a while, have a good time, most students will actually be very conscientious. And you say, please execute these tasks, they'll do the right thing. A small fraction of the students will not be conscientious and simply blast through as fast as possible because it's a time value of money kind of thing. If they get out of there in a half hour instead of an hour, they just doubled their money. So we had to actually change the incentive function to give them incentives for accuracy and time. It was interesting, the impact. So I'm moving really fast here. You can interrupt me if you like. So this is sort of a summary of the first half of the talk in sort of one piece. This is so the condition where you don't use the virtual information officer is just a classical content management system. And that content management system is exactly the forms that you saw. We just simply stripped out the interaction tricks that we had and stripped out the machine learning. So it's actually a pretty good form system if your job is simply to do data entry. Certainly far better than the equivalent system that CMU uses at the moment, which was built in the 80s or something. It's a disaster. So then this is the rank of participants by condition. So this is the rank of their total task time. So this is the fastest user in the VIO condition, and this is the fastest user in the CMS condition. Okay, and you can see that if you order people this way, there's this clear separation all the way along, except for this guy, who of course was a complete idiot. Unfortunately, Murphy's Law says that the complete idiot always ends up in your condition, not the other one. Essentially these lines are parallel, and our interpretation of this is that you're getting a fixed performance improvement, essentially independent of skill. So you could sort of interpret this as a measure of how skillful you are, and lo and behold, it's helping you everywhere along the spectrum. So if you're an expert user down here, this gap compared to this represents about a 31% improvement. And if you just aggregate everyone together, independent of their rank, you get a 17% performance improvement in time. And those are both statistically significant. And there's no statistical difference in terms of errors. And there's a lot more detail and a lot more slides, sort of data that we've extracted in these two papers, which I encourage you to read, or you can just ask me, and I'll tell you. Okay, yeah?
How did you measure errors? Was it just strictly the number of errors, or were you looking at the severity and the types of errors that they were committing?
Oh, yeah. There's a long explanation and a detailed analysis of the kinds of errors they were making. And it turns out that if you go back to that original message of Blake's, and you look at the form, there's two ways of interpreting the correct, you can't really see it here. There's two ways of interpreting the correct update. One would be to just change his title and ignore the fact that he's got a new room, because it's not really clear that that's part of the update. And some people didn't actually add that, and we decided to count off for it. We decided that you had to be a conscientious user and use the most complete update. There was another example where there was data actually squirreled away in the signature that wasn't in the actual message, and again, there was a question about, is this a legitimate update or not? And we decided to be as strict as possible, just because we had to pick some rule, and that seemed to be the one that was the most conservative. Okay, so now we're going to leap forward. Well, the original work for this was done about the time that VIO was done, a little bit later, but we've gone through sort of several revisions. But the objective here is to provide a way for people basically to specify the kind of information that they'd like to have to solve a particular task, and have that sort of automatically attached to the message. So again, if we went off and did a contextual inquiry and asked people who have office assistant jobs at a university what they did, and they do an amazing amount of work that I find horrible. A typical example is, what are all the midterm grades of the students in my degree program. That's 420 students. And it turns out the IT system doesn't give you that answer in a nice little list. The only way of getting the data is to look up each person's individual record. That takes 5 hours for someone to do. And she does it every single semester. Okay? This kind of tool, and this is a quote from the person who was in the study who had this job. She said, with this tool, I could solve that problem within 5 minutes. And we actually think that's true. Another good example, which shows up later on, is the associate dean for one of the programs gets an email about once a week. It's someone who's broke their leg or got arrested or whatever. For whatever reason, they're not going to show up in class. And so what this person does is send a message to every instructor of this student that the student is unavailable for whatever reason. And the quote we get is that takes 2 hours. And again, they're essentially, if you know SQL and databases, they're simply doing a join across multiple tables, but that information isn't readily available, and they essentially have to repeatedly navigate the join by going to various data sources. Okay? So this is what we want. I'm sorry this is too hard to read here. We have a visitor from Korea tomorrow. He's interested in how we teach, so I thought I'd have him sit in on 21369, section A meets tomorrow. Can you tell me how many Korean students are in this class? After using this tool, there's a script that's generated. It's effectively a program. You can think of it as a sequence of SQL queries that will be recognized as relevant to this particular message in the same way that form selection is done in VIO. It will be executed automatically. The results will be attached. Now, of course, we're going to make mistakes. Turns out the penalty for a mistake here is completely different. All you have to do is ignore the data. So in VIO, you want it to be very high precision at the expense of recall, because if you made a mistake, people might have to type or do something. Here, you're probably going to want to have lower precision and higher recall. And what I'm showing you is a mock-up. This is the VIO stuff is about ready to be commercialized. This is still in the, we have the front end actually operational, but the back end isn't. Okay? So the question is, how does it work? And now you're actually seeing the front end, which we've built. Here's a copy of the message, and you get what is actually, you can think of as sort of a mini Excel spreadsheet or a very stupid Excel spreadsheet. And it just says label and value. They're empty. There's no table name, and there's a little thing that you can hold here to drag. You drag it across, and you fill in all of the columns with the data that you need to solve this particular query. So what's the course number? What's the section? What's the course title? What's the student's last name? What's the student's first name? And what's the country? You don't actually need all of these columns to answer this particular question. And there's some variety here about what you could actually do. So one of the first questions is, are people actually capable of conceptualizing a table which would contain the data that they need to solve a particular problem? It's sort of a very fundamental question. And we did actually first paper prototyping and then a study using Excel to actually convince ourselves that they can actually do it. So essentially, office workers who have these kinds of problems, who deal with information systems, have actually a reasonably good model of what's going on in their heads. Now, it turns out that there's all this other stuff that's in their heads that you don't want to acquire. For instance, we don't acquire the aggregation function of counting. We don't acquire the fact that you want Korean students. Okay? So there's this careful line about exactly how much information you're trying to extract to solve a particular problem that's in that person's head. And the reason that that's important is a lot of that information is changing over time. For instance, another person we interviewed, the incoming request was, please add pen fan to my Studio 2 course. Now, it turns out that seems like a simple request. It's not. There's this complicated bureaucratic procedure that has to do with, is this student a member of my degree program or not? Is the student on the wait list? Does the student take 30 credits or more? If they do, they have to fill out a separate form. So these complex procedures, which essentially is the real job of an office assistant, to maintain those procedures and understand how to execute them when they're given requests. We don't actually want to capture that information. It's too expensive. It changes too much. So here we're focusing on essentially a very narrow interface that gets them most of the way to where they want to be and saves them a huge amount of time. Okay, so back to what you do. What you do is you take the section number, you copy it into the course number column, and then of course you've got to go off and navigate to the IT system to acquire all this other information, which is what you would be normally doing to answer this particular question. So here is a copy of the student information system that we reproduced because we couldn't use the production one, obviously. You're selecting class roster, you're putting in the course number and the section number, and you're getting a listing of these people. You're going to copy the title of the course into the course title. You're going to copy the first name and last name into student first name and last name. Here, then you're going to select a student and look at their bio screen display. It's amazingly bad interaction, but we pretty faithfully reproduced what the actual system does. And then you get this other page, and lo and behold, their nationality is right here, and then you have to copy and paste that into the country field. Now remember, that clunky interaction of 4 screens, you'd actually be doing for, no matter what. You're going to be doing that anyways. And then what you get is this wonderful single line that you've demonstrated of the information that you want, and then you're going to use this fill in table button. And this works conceptually sort of like pulling down a marked set of cells in Excel. It essentially says to the system, do what I've told you to do over this set of data. And here, it's like, okay, go fill in the table, right? Here, I gave you an example, go do it. And what we've done in the back end, or we will, and we've got this working with a different front end, is we simply record the sequence of database calls between the application and the database. That gives us a listing of SQL and results. We actually can go through there, find all of the constants that are relevant, turn them into variables, and give us a program to execute. Because of course, that's the ultimate goal, is the program, that the person implicitly told the system they wanted to execute by going through those navigations. It's a lot like a macro recorder, just a little bit smarter. Okay, and then what they'll do is they'll hit fill in the table, and the system will do exactly the procedure I described, generate this program, and do this retrieval, and here you get all the students. Okay, and the stuff marked in orange is essentially a signal to the user that says there were multiple possibilities in this particular location. So when you tell me fill in the row and this thing, those are the ones that I'm going to expand.
How do they tell it which things to hold constant and which things are the variables?
It turns out you can tell by looking at the script. It's just the fact that when you follow the variable that appeared in a particular answer, it ended up in a result set of a query, and so you know that the next time you're going to execute that query by replacing something in the actual query itself, you're going to get a different number of answers. So you can figure it out.
As they would have done before. So for example, if the question would have been to them, I need to know all of the, the classes that Barbara Adams is in, they would have gone about doing that a different way.
Yeah, they would have solved a different query, and then you would have gotten, in fact, that's much simpler. Presumably the interface would support that much more directly. One would hope, but actually with that, yeah, with this system, we're actually not that sure. And so you could fill in the table here, and it turns out that from this interaction, there's something, this is actually the training interaction for the actual experiment that we're running now, but there's a subtlety, which is that if there's a set of choices in the email, those are simply legitimate ways of filling in a particular row here. So if you had 2 section numbers, then you would have gotten an orange here, or 2 section numbers, you would have gotten the same course number, but orange here, and presumably non-orange, because probably the course title was the same for both sections. And if you had 2 different course numbers, it would give you another set of rows here, which are the other course, the sections, the course titles, and all the students there. And in fact, the reason that that's critical is because people send spreadsheets to each other. And what we want to be able to do is drive the execution of the actual program off of rows in a spreadsheet. Okay, and that turns out to be sort of a very powerful next step. And when we went and talked to customers and showed them VIO, they said, oh, this is great, but it's only point-wise. You're only doing 1 update per email. What happens if I get a spreadsheet? Or what happens if I buy a customer list and I want to update this stuff? And this invokes, in my background, all of these questions that are currently being researched about federated databases and applying machine learning to federated databases problems. Data cleaning, that kind of thing. Anyways, so the idea, of course, is that if you get another message, here this is a bad example because the text is identical, but if you get another message that the classifier decides it's the same script, it will do the extraction of the course and section number and here execute the query again. Okay, so it turns out that we're using end user programming, which has some great power, but if you know the literature, there's sort of a long series of programming by example car wrecks in the literature. Many people have built these systems, but they're very, very difficult to actually deploy and work because they've got these tricky problems. One is, how do you get conditionals into the system? How do you get an if statement? How do you terminate the loops? How do you figure out when things are terminated? And we actually have sort of solutions for these questions. But it turns out, we think, a good paradigm for these administrators who seem to be able to understand how to manipulate this kind of system. Okay. One thing that we do that's different is there's no requirement that you get all the exceptions right up front. You can simply execute the system, and if it breaks at a certain point, the system will come back and say, I'm sorry, I don't know what to do here. Can you just simply demonstrate a little bit more retrieval to fill in this part of the data space? And then what it'll do is take the two scripts and scissor them together using a conditional. Right? You're aware of that, or you've seen it before? I'd like to know where you've seen it.
I just thought that was nice.
That's a hard problem. And another example of this Korean thing where we don't think that programming by example is a good solution. Suppose you really wanted, suppose you had 10,000 students, or suppose you had 1,000 students. You don't want to read through 1,000 students to figure out who's Korean. You could just turn this bar here into the list manager of Excel, which is this, I don't know how many people are familiar with this. It's sort of a subsystem of Excel where you're allowed to do searches and selections and things like that. So when appropriate, we want to stick in direct manipulation. Okay, so just one comment for non-design people. Design people will be very, very well aware of this. This is actually a screenshot of a particular user trying to fill out a form based on a message. And that's what we did to figure out the basic questions of how to do the interaction here. There are other many tasks that we think we actually cover. Give me a phone number for everyone in New York City. That's probably not such a great example, but this is something that's been mentioned before. How much money is left in the travel budget? That's a question I ask every once in a while from my office assistant, and I'm sure that question in CMU is asked probably somewhere at CMU every day. And obviously these scripts, once you create them, you share them, which we haven't done a lot of work on. We plan to do. There's a related project at IBM, which is incredibly good work called CoScriptor, where they really focus on collaboration more. And this one came from a student. Get Me the Yards carried last week for every running back in the NFL. He's a fantasy football guy. It turns out that he was doing this complicated retrieval every week. Now, if you understand the back-end issues, this thing turns out to be much, much harder to do because you need to be able to scrape websites. And there's this whole question about extracting information from websites, which in a corporate environment we ignore because we have access to the JDBC driver. But that's a whole separate discussion about sort of where this functionality can be deployed. And here are some results hot off the press. There's a grades problem, which is give me the grades of these students. There's this sick scenario, which I described before, get me all the email addresses of the instructors for the classes of this particular student. And what we do is we give the first problem, and then we give the second problem. So this is the first task. This is the second task where clearly the mixer program is being invoked. So the amount of time it takes to do the task is, of course, vastly different. This is not even really a fair comparison because you have to go through and do the thing manually here, and the program is being executed on your behalf here. But I think the really nice thing about these results are that even the first time you solve that particular task, it's faster to use the tool than it is to do it manually. And the key question about one of the key questions about these systems is adoption. is the barrier, the initial barrier using the tool low enough that people will actually use it? And this has crushed many a system. And we think that this is a really good incentive function. If you can convince people that it's not going to take them more time to use the tool than not use it and ignore the fact that it generated a script, it's still going to be faster. This, I think, is a great incentive. And the reason this is true is that it's going to take you a little more time to build that table, but that calculate rows, the extra time it takes to do that is saved by the calculate rows button. And here there are 4 rows in the email, so you're going to have to do some kind of retrieval 4 times. So the trade-off is somewhere a task size of around 4 items. Okay, and it's obviously complicated to measure tasks, but I'm trying to give you some understanding of where the break-even point is. Obviously, if you had only 1 retrieval to do, the tool wouldn't help you unless you predicted that that particular retrieval would have to be done again, and then, of course, you would get this benefit. But that would sort of require some proactive behavior on behalf of the user, and now you get into this whole sort of psychology of the user. Are they mavens? Are they somehow, is their identity attached to using technology and all that kind of stuff? Are they a laggard, in which case they won't think proactively? And we don't want to get into that space. We sort of want to convince everyone that anytime you want to do navigation, just use the tool. Okay? And there's so much related work here because we're drawing on so many different areas. I just wanted to call out some things. There's some automatic form filling work. There's this famous work by using forms in communication from Malone. Lookout is an example of, by Horvitz, which was an Outlook extension that was trying to proactively help you use mail. Eager, which is one of the very early systems and programming by demonstration, well, not early, but an interesting programming by example system. There's lots and lots of work on email and personal information management. There's obviously these natural language processing things, and then this reference here, Clio, is to a data integration problem, because going back to this, this is a real leap here for people who aren't familiar with this. You can think of this as building a mapping between a source set of tuples and a target set of tuples. And that's what Clio does in the database environment. And then I can talk a lot about other things that are related. One is Google Autolink. So some people might not be familiar with Google Autolink. If you have the Google desktop loaded and you're on a page, there's an Autolink button. You click that button. It scans the page for addresses, replaces the addresses with a link to Google Maps. It also finds things like UPS codes, FedEx codes, that kind of thing. So from an abstract level, it's the same kind of problem. You have natural language text, you have a model which you're applying to it, and you're presenting a form as a result. Of course, that form is a URL, not a bunch of field value pairs, but it's still the same paradigm. Obviously, Google Mail will recognize calendar events for you, ask them if you want to add it to a calendar. These are sort of all related behaviors. Even Microsoft's Clippy, which is sort of a famous example of how not to build these systems, is an example because it recognized Dear John, comma, which is a natural language text document input. It applied a model and said, oh, you're typing a letter, and then it presented a form in a very irritating way that said, yeah, can I help you with this? And as you pointed out, it wasn't even clear how it was helping you. And then you proceeded to beat your laptop to death because it was so irritating. In fact, Clippy was such a failure, Microsoft ran commercials advertising the fact that Clippy was not available at Vista. They were actually advertising the death of one of their products to sell the next generation of their products. That's an amazing thing. Or at least I've seen YouTube videos of things that convinced me. They were professional quality advertisements that were doing that. So I believe it. And then the last one, which is maybe the grandfather of, well, not exactly the grandfather. There's something called QBE, Query by Example, which is a very famous system, which is Microsoft's Access interface is very similar to, done by Zloof. And here, this is not programming by example. Users actually essentially construct variables. But it's very similar in sort of in its interaction flavor in other ways. Okay, so I think I did that in like 30 minutes. I don't know what time it is. Any other questions? Yeah.
Can you talk about a bit about the features you're using for the machine learning algorithms?
Yeah. So for VIO, the first one, as I said, we're using essentially the default set of features that show up in the machine learning algorithms. So here, for form suggestion, what's called the wild label, which is the interaction label that you extracted, is the form that you actually selected. And then we have a process called domestication of the wild label. This is something we sort of inherited, which is generating the actual label we use. That's pretty easy because you're just flagging that category as the label. And we're using a bag of words representation for a document here, plugging it into a K-way classifier. I think we use naive Bayes, actually. But you saw the experiments. We tried a bunch of different algorithms. And then here's the key thing. You're going to threshold those. You're going to compute likelihoods and then threshold, because remember, it's high precision. If the system isn't confident and knows what form it is, it's much better to say nothing, because there's this whole question about extra labor involved in fixing anything that the system does wrong, and also building trust. If the system is almost always right, you're going to tend to believe it. Okay? For field suggestion, the field value that is in the form, so that RM space 390 room number, is then used as the wild label, and we scan the input message, find that string, and label that string in the input message as the gold label for that particular extractor. And then we use state-of-the-art here, conditional random fields over documents. The conditional random fields is state-of-the-art sequence learning. And then instance suggestion here. Oh, I'm sorry, you asked about the feature space. So it's things like, it's a standard set of features. It's like, this has only digits. This starts with an uppercase and then has only lower cases. This has uppercase, lowercase, uppercase. If you read sort of information extraction papers, there's sort of a collection of features that are typically used. Now, the rule here was no specific engineering at all, because we wanted to avoid the game of secretly adding features to improve performance. Or not secretly, but it's very easy to look at the input data and say, oh man, I just missed one thing here. So we banned anything. We do make one exception to that rule, which is that we use a last name dictionary and a first name dictionary, because it turned out it doubled performance. And so we broke that rule for that one instance. But for instance, for titles, like research scientist or whatever, what we do is we read the set of titles that are already in the database and use that as a dictionary. So that's how we get around first name, last name, and all the other fields. And since you're asking, and then the last one, instance suggestion. Here you build a vector of all the extractions. Then you take that vector and compare it to every tuple in the database and compute a delta between each attribute and that particular instance. So for instance, and score it. So if you have the same first name for that particular attribute, you'll get a 1 as a score. If you have a different first name that has no overlap, you get a 0. And you do that for every single attribute. Now you have a bunch of vectors that tell you the difference between your input value in each instance in the database, and then you can run any machine learning algorithm you want over it at that point, because it turns into sort of a classification problem. And that's just the general scope of the algorithm. That's obviously too inefficient to do in a scaling way. We have ways of making it much more efficient. And it's very close to duplicate elimination work that's done in machine learning. And since you asked that question, you get a freebie. I'll give you some more data. Here we are. So here's extraction performance for a bunch of different categories. This is bios. It turns out this is just a side effect. All the bios were almost identical. Here's our ability to recognize an email over time. Here's our ability to recognize a first name over time. This is a last name here. And then this kind of effect here, that just turns out to be a side effect of the fact that the test set had only a few examples. So you're getting really high variance. And just to explain this, this is the number of examples that show up out of 180 messages. So actually every message here contains a first name, but some messages contain no last names, because this happens here. And obviously, if you're on the left-hand side, you have so few examples, you get bad performance. And if you get a lot of examples, your performance basically goes up, not surprisingly. Now, the key thing here about this is that even though the performance is all over the map, the user still is more effective. And there's this underlying correlation between the fact that the stuff you've got to move that appears often in messages will obviously end up being examples that occur often, so you get better machine learning sort of focused on the areas that you're actually manipulating. Okay? So yeah, if some weird field is in that form that you fill out 1 out of 1,000 times, it's not going to be able to predict it because it's not going to have a lot of evidence. That's not surprising given the rules that we have. Okay? Another question so I can give another surprise. Yeah.
Mixer question. So, since you are interested in the federated databases, are you? Is there sort of a meta level where you see that they're basically doing the federation for you across, like, say, siloed databases?
Right. That's nirvana. Right. Where you would take the logs of the access to 2 siloed federated databases, scissor them together, and run the program across both of them. Yeah. And I actually think that that's the way to do data integration now.
Right. And so the next person that comes in, that view is pre-created, as that's where they start on that view?
Yeah. I mean, that would be a fabulous thing to try. We actually tried comparing a previous version of Mixer head-to-head with Clio, which is a direct manipulation interface, where on the left-hand side you get the source, on the right-hand side of the screen you get the target, and the interaction is simply drawing lines. And we were trying to beat that. And it's not quite as fast, so we couldn't publish it. But we actually think that with a little bit of work, we can at least tie an engineered, explicit, expert interface for doing data integration versus something which the vast majority of people can't understand, versus something that everyone does every day, which we think is a pretty important demonstration that maybe people ought to be thinking about the federated database problem in a completely different way. I spent 3 years building federated databases where the target was the programmer and you were trying to give him a better script. But instead, in fact, a lot of federated queries are actually being executed every day by office assistants, right? They essentially do it by hand, so why not acquire that labor and use it? But it's we're years away from that. And it turns out that what actually happens is, right now we use the JDBC driver, the next version we'll use an abstract engine. So we'll separate ourselves from the driver and use an abstract engine. And then you can plug in operators that do fuzzy matching and all that kind of stuff, because you can't do fuzzy matching in SQL. It's almost impossible. You could bury it inside of the database, but people don't do it that way. They have application programs that do it. Good question. Okay, I've emptied the room.